Okay, so I think all of you will see my slides. Okay, if you cannot see my slides, I will check for the first 10 minutes. Okay, so I think last week we shared about the memory, and I did some tutorial on the memory, and this week we will focus more on the I/O system. Now this lecture, you might feel that it's actually very trivial, but this one is actually very important because the rest of the components like memories and stuff, you have a vague idea, but when it comes to memories, a lot of questions can come out. And this I/O, right? I/O is it's very embedded system. Okay, so the rest of the stuff like computers, whatever, they share the same structure, but when it comes to I/O, okay, I/O is more to embedded system. Now what is first of all, what is I/O? Okay, I/O stands for input and output. We know that the embedded system microcontroller microcomputer is nothing but a computer with a lot of I/O pins. Okay, I/O means input output pins, where you can actually communicate with the rest of the devices, whether it's a motor or a printer or LCD or whatever. Now these kind of things are very important because it helps you to be able to build stuff. So after this is your second year, third year, fourth year, you might want to get involved in FYP. All right. So this is where your knowledge on how to do certain interfacing will become very handy. All right. So some of your friends you might see that their FYP projects involve a lot of interfacing with LCDs. They design a certain equipment. Even in the third year units, like capstone unit, right? Like a design project, you might need to come up with, you might acquire this skill to be able to build your own devices. Okay, so this is very fundamental. If you guys are involved in an industry where you require to design heavy interfacing, for example, you're designing an embedded system for cleaner for Sony, Panasonic, for all these kind of companies that you involve in, whatever that you learn here will be very applicable, not only on a theoretical level, but straight away you can be able to use whatever that you learn in this unit. Okay. Today's lecture will be doing a case study. We will be more on using how to do a Texas Instrument I/O, right? But the knowledge of I/O is more or less same. Okay, if you have the theoretical basics for say Texas Instrument embedded system, okay, you're able to do other stuff like Arduino or microchip or whatever brands that you come across, Freescale, So we want to learn more about theoretical, but I hope that at the end of the lectures, at the end of the semester, you'll be able to have hands-on experience. Okay, so today you guys will be doing loading a program, and then observing the LEDs. Okay, so that is actually part of the I/O. The LEDs are actually connected to the pins in the microcontroller, Texas Instrument 430, and you manipulate the LEDs, okay, based on your programming. So, but whatever that you're doing in lab is actually quite basic. Okay, we'll be going more in depth, and the tutorials will be even more in depth. How do I do? What are the techniques to actually manipulate the I/Os? Let me check the. Okay, so no chats. Good. All right. First of all, we want to have an overview of whatever that we're learning today. We'll be going to an anatomy of the whole I/O system. When we mention I/O, actually there's a lot of things. Just like, for example, when we mention CPU, there's a lot of mechanisms inside CPU that we need to study, all right? Sometimes we're living in this era where we take for granted how complicated things are inside every single machine or mechanism. Okay, we take for granted because things are all given today to handed to us. If you want to if you want a microcontroller, all you need to know is basically C programming, and then you do stuff on your Arduino, everything is done. But actually, how do they work deep inside? That's very important. Okay, so there is always this case study. This lecturers during my time, they always scare us. What if there is a doomsday? Everybody dies, and you are the only engineer available. Okay, how are you going to actually rebuild? Rebuild everything from scratch? How are you going to rebuild the basic stuff that we have, like for example, a pen drive, cell phone or whatever? This is a case study. This is a very interesting question. What if you are the only engineer around and everybody have all the other technology companies have disappeared? How are you going to rebuild society, all right, with whatever knowledge that you have? So this is just a case study to encourage us to find out more fundamental about stuff. All right. So we know Arduino. Most of us have interaction with Arduino because you have your EN 1000 electrical system. I think most of you have a hands-on experience at least for one lecture. And some of you have fundamentals of digital design, hardware design. That's also very, very important unit. So we need to know what's inside the I/O system. It's not as simple as programming, just one line of code and then the LED goes on and off, something like that. It doesn't work that way. There's a lot of intricacies involved. Okay. We're also going to talk about parallel and serial processing, the I/O. Okay. We are not. We are going to cover about what are the advantages and the disadvantages of serial versus parallel. Okay. Traditionally, when you want to interface with devices, you can do it parallel or serial. Okay, so there's two ways of doing it. If you want to send information, 8-bit information to another device, you can send it using parallel or serial. Okay, I think you understand what's the meaning of parallel and serial. Okay, so parallel is, of course, the speed is faster, but there is a downside to it. Okay, parallel ports, you need a lot more ports. Back in those days, probably the time that you weren't even born, printers used to come in parallel ports. All right, so the printer cable is extremely big at the time. If you have some spare time, you can actually Google up some of the early versions of printer. They are very big. The cable is actually much bigger than what it is today. Reason is because they send information using parallel ports, and some of these ribbon printers are still using a parallel port system. Okay, so there is upside and downside. If you use a parallel processing, things will be faster, but it will be much bulkier. All right, and serial processing, sending information through serial, is another alternative which reduces the amount of pins. So your USB, for example, is a form of serial communication. Okay, although you do not know, serial communication has gone through a lot of alterations, evolutions. Okay, so what we have today, I2C, SPI, USB, are all from the same technology. They call it the serial processing. In fact, I'd like you guys to just look at a few very important, namely the UART. UART is one of the very important and very basic serial communication. In fact, it's so basic that most of the military applications, like for example military radio, and even terrestrial, our radio base stations still use serial. Okay, but serial has totally disappeared from commercial computers. But if you next time you guys are doing some work for radio base station for telco, serial port is very important because you will be able to program the radio base station using serial. Okay, there's a reason why these people do not want to use USB or I2C or SPI. There's a reason for it, because in a war zone or in very high level devices, they do not want so many types of software interface. They want it to be as simple as possible. Okay, so this is something that you need to consider when you are actually, if you guys do involve in designing military devices. There is no such thing as USB or whatever in military. Okay, everything have to be serial communication, as the interface has to be as simple as possible. Okay, you do not want, when you open the laptop, oh, okay, this is a Windows 10 or Windows 8, I cannot go to war, okay, because of this. No, that's why serial, it's much preferred. Okay, the higher the importance of the industry, they will go for more serial communication rather than all your USB ports or whatever. I/O and CPU interaction. Okay, I think you know a bit about this. We've discussed on the memory I/Os. Somebody text me. Is it you guys? No, not you. All right. Okay. If there's any problem, you can always text me. My cell phone is on, so that I can. Anything happen, you can text me. All right. I/O and CPU interaction. So you have your buses and so on and so forth. And we know that this I/O has something to do with memory inside. Okay? So if you want to control, let's say for example, a single pin in a microcontroller is always associated with a memory. And when it's associated with a memory, we know that based on last week's lecture, we have the buses. Okay, so that's where the buses will be important. Okay. Timing diagrams. This one is very important when it comes to SPI, I2C. I will explain further on that. Okay, but SPI and I2C are variations of serial communications that requires timing, because you might have two sets of device, that communicate with the same master CPU and etc. So this is why you need a timing. How do you design a protocol, a rule-based or interface, protocol to be able to control multiple devices at the same time? So they have certain rules. Okay, this guys is working on different timing. How do they synchronize that time and so on and so forth? This is a topic of discussion which is very important. Okay. Now, I/O system is a combination of all the devices and peripheral connected to the system bus other than memory and CPU. So anything to do with communication with other devices, memory and whatsoever, other than the memory and CPU, that one, it falls under the category of I/O subsystem. Okay. Now, okay, let's take for example, connection to LED. I/O or not I/O? Definitely it's an I/O. Okay. Connection to motors, I/O or not I/O? Okay, they are not memory, they're not CPU. Okay, so they are I/O. All right. Connection to LCD screen. Okay, so there's another form of I/O communication. So whatever that you can think of, communicating with the printers or whatever, anything that that interfaces with world objects, sensors, motors, actuators, sensors, these are what we call I/O. At least you have to be able to acquire the skill to do this basic stuff. Okay, communicating with world devices, outside world devices, sensors, and so on and so forth. Peripheral devices serve as either input, output, or both. Okay, so you can see sensors serve as input, they extract information. Motors serve as output, they call it actuator. Input, sensors, motors, actuators. Okay, and some devices, they function both ways. Okay, they are probably high level devices. For example, motors. Okay, some motors, they give feedbacks. All right, they give temperature feedback and so on and so forth. So these are very high level actuators that can you can output and you can have input at the same time. So the same device, you can make it to do something, but at the same time it sends you certain certain information. Okay, so normally high level devices, like for example flow meter. Okay, flow meter is an input lah. It's not an input output. Okay, so if in the devices that give you information, you call it input or sensors. Devices that takes information and do something, you call it actuators. Normally there is a form of motor or whatsoever. Okay, devices that have both, you call it input output devices. All right. Okay, very short example. Can you guys think of anything that has input output? Okay, so input output. Okay, I'll give you an example. Okay, radio devices. All right, so radio devices, for example, your XV, Zigbee, or whatever. These are radio devices. How can I communicate with, let's say, for example, a drone? Okay, a drone, feedback drone. All right, so your drone will require to send information to your radio, and your drone will also receive information from the radio. Okay, video feedback, right? And you want it to control the drone to fly certain directions. So this is an example of input output. Okay, radio communication is an example of input output. Okay, so Zigbee are input output devices. Can you think of anything else? GPS, right? Now GPS, why I call it input output? Because GPS, if you guys have played with GPS module before, serial GPS, communicating with embedded system, you will know that you can actually do setting for GPS. You can send an information to the GPS module, what type of information you want. Okay, so after you extract the information, you do processing the GPS string. You do a string processing system to extract the information that you need. But GPS is an input output device because you can do setting, okay, with the GPS. Okay, special register devices used to manage a system operation without external are also part of I/O. So these are special classes of devices. Okay, managed operating system without external system are also part of I/O. Is also considered part of I/O. Okay. So this one I've actually explained. Input transaction means to say that an action with a sensor, a transaction with a sensor. You know what's the meaning? The word transaction in English means a process. Okay, so if you do a trading, okay, with someone else, is a transaction. Okay, if you take money or you send money, is a transaction. So this word is actually used in this context. It's an input transaction. It means to say that device send information to the CPU is an input transaction. Okay, device receive information from the CPU is called an output transaction. Okay, so we use this term. Okay, if information is moved from the outside sensor to the CPU, let's say for example, analog detection, analog proximity detection. Okay, if this information, proximity information, is transferred to the CPU, that's an input transaction. If it's transferred from the CPU to the motor driver, that's an output transaction. Okay, it's very simple. I'm not going to go in depth with this because very basic. Okay. Now, what are the input devices that we can think of? These are a few examples. So this is probably the earlier versions, the earlier courses, your connection with all these kind of embedded system. This is probably one of the earlier units. Okay, if you continue further, you FYP and all this, you will have more hands-on experience. Okay, so but these kind of things I hope that you have actually seen before, doing some basic interfaces. If you've joined our IEEE clubs, so on and so forth, most probably you're quite familiar with all these kind of things. Okay, so switches and keyboards. Okay, switches. Okay, so if the most basic device is actually a switch, many of you have used switches, but there is some group of people that they build the switches using mechanical switches for gaming. Okay, for gaming, so they want the tactile feedback, so they use switch. Okay, for gaming, and this switches, every single key in the keyboard is connected to one on-off button. It's a physical mechanical switch, okay? And these devices, normally they have a logic, an interface circuit that communicate with the PC, all right? So you need to design an interface logic, okay, for these switches. So switches, whether they are mechanical switches or silent switches or whatever switches, or keyboards, you know, they're part of input devices. Means to say that when you key in, okay, the CPU actually reads the ASCII key, all right? So every time you punch, let's say, for example, the letter A corresponds to a very specific logic ASCII code, okay? So that we always have a table, okay? The letter F, upper caps or lower caps, you know, what is the equivalent, you know, in binary or hex, okay? So we always have that 8-bit information. This is where we use switches and keyboards. Switches and keyboards, you need priority. You given CPU will be given priority to keyboards and switches because it's user interface, okay? So when you're designing embedded system, you always remember anything to do with user needs to be given priority, because when you're designing a device, you do not want the user to keep waiting for a very long time. So once the switch detects there is a bit of changes or there is a bit of movement in the key or the keyboards, you always give priority to the CPU to receive information from the keyboards, okay? So that's common sense. Anything to do with user, you designing anything, you need to give priority to the user input from the switches or the keyboards, okay? The second thing is barcode reader. It's a form of input device. All this kind of stuff you can actually buy and fiddle with it, okay? You can buy from websites, okay, to play around with the Arduino or the MSP430. You have your position encoders, all right? Now this one, it's I can give you one example, wheel encoder. Motor itself will turn, but the motor itself does not have feedback how many turns that it has actually performed, okay? So there is this thing called rotary encoder, which is very important in the industry, not only for hobbies, all right? For hobbies, you want to know how much the motor have turned, okay? So that's a very simple example, but in the factory, all right, if you're working in a manufacturing line, you must put a rotary encoder to know how much it has changed, okay? Analog to digital, digital to analog, in both ways, ADC, DAC, all right? So these are, you have a sensor that gives you an analog voltage, okay, based on your proximity or your temperature or whatsoever. This logic level, this output analog level will be converted to digital. Okay, so this is actually very important for a lot of devices. There's a lot of devices that, I mean, for those that are using low-level proximity sensors or temperature sensors, they still prefer these analog to digital converters. All right. Some of these SPI or I2C, we call it digital sensors, are actually not so trustworthy. Some people, especially in the area of instrumentation, okay, if you are an instrumentation engineer, you have to know this. There is no choice, all right? What is the precision level, okay? So what is the steps? So probably this one I will cover in the tutorial, okay? This one is very important, analog to digital. If you guys are doing instrumentation, you need to know this by heart, right? Example of output devices are LEDs. What you're doing in the lab, okay? The CPU sends an information. You program and the CPU sends out information through the LEDs. That's a form of output. Display, buzzers, motor interface, digital to analog converters. All these are output devices. Means to say that the CPU sends information to the devices that are actually doing something connected to the world. Okay. So printer, you can see, you look at, you deconstruct a printer. Printer is actually an input-output device because they consist of output devices, okay, and actually input devices. All right. So for example, the printer actually gives you a status whether it's you're having error or whatsoever. So you know, printer is an input device, but printer is also an output device because when you press print, the information is sent to the buffer, and the buffer actually prints all these kind of things using the motor. All right. So I hope that you can differentiate between input and output device. You have serial example that are both input and output. Okay, so this is the example given. Some device you communicate to receive and send information, like what I mentioned. GPS is a good example. GPS gives information to serial, okay. Bidirectional ports, okay. So these are all communication device. Most of the communication devices like radio communication, optical, whatever interfaces, most of the communication device can be categorized as I/O, input output, okay. Pen drive is input output device. You read and then you also write. Okay. So this is the picture that depicts. All right. You have your input and output device, but some of these are actually very weird. Like for example, I mentioned printer. Printer, they categorize it as output. Okay, according to this slide. But if you really think about it, printer also sends information. How's the status of the printer? Has it finished printing and all these kind of things? So printer is more suitable to be categorized as input output. Okay, devices. You know. Now, those are common sense stuff that because most of the equipments you deal with in your daily life, right? Now, these are the things that this could be the first time you're listening to me talking about all these devices, something new to you, right? So what are actually some concepts associated with I/O are timers, watchdog, communication interface, ADC, DAC, and development peripherals. Now these are something that we will go along as we study more. You will get the hang of it, how to do an ADC, design a system which has the best precision for the embedded system. Okay, so let's say your sensor is 0 to 3.7 volt. How do you actually do the conditioning? That's where you need to know what is ADC, DAC, right? Timers is something that you hear probably for the first time. Okay, inside your embedded system, there is a module called timer. Okay, now timer is used, let's say for example, you want to check a device every 1 minute. So you do a timer in your code, and you do the setting. Every time your device reach 1 minute interval, it will actually check the device. Let's say for example, give an example, proximity sensor. All right, do you want it to check every half a second? So that will actually not necessary. Some things do not change very fast. Like for example, certain machines status, they do not change very fast. So practically you do not need the sensor to check the sensor reading every half a second. Okay, you can do probably 1 second, 2 second one time. Now that is where you need the knowledge of how to set timers. Okay, what about watchdog? Now watchdog is important because watchdog timer helps you to reset your embedded system. Okay, let's say an example, you're designing a telemetry system that keeps on streaming information. Now, sometimes just like any machine, sometimes your device get hang. Okay, you cannot actually go to the site and reset it. Your watchdog timer can do that for you if you program it nicely. All right, if you know how to do it, you program it nicely, you'll be able to do this. Okay, I'm not going to touch specifically on timer and watchdog because subsequent lectures you will cover this really in depth. Okay, but we're probably going to look into other stuff. There is a dedicated lectures on timers and watchdog timer. Okay, If you want to read earlier on this timers and watchdogs, you can check out week 7 or 8, okay, of the lecture slides. All the lecture slides are actually in the folder. You can check it out. You can unzip it, download everything so that you don't have to download week by week. Okay, everything is there. All right. Now, timers, they can be programmed for prescribing any time interval, but you need to know how to do it. Okay, we know that you need time, you need a ticking. Okay, and we have this device called oscillators, crystal oscillators. It is one of the most important, the life-changing material that we ever encountered, that has actually changed the whole face of electronics. Now, why do we say that? In order for the embedded system to be able to process, you need a time, you need a clock, okay? Something that gives a pulse, okay? Now, everything is digital. How do we get a pulse, okay? So some time ago, some people, they actually found that this silicon or germanium, when you press it, you know, quartz, sorry, not silicon, germanium, quartz, okay? So quartz, when you press it or something like that, it gives you a pulse, okay? So this quartz, hold on. Yes. Yeah, I'm having class. I call you again. Okay, okay, I'm having class. I call you later. All right. Okay. So the timers can be programmed to check the status of sensors at a certain time interval. Let's say, for example, you want to check 1 second interval. You need to know how to manipulate the timers that are actually available in your. There's only one source of clock, which is the oscillators. Okay, the clock. Okay, so you need to know how to manipulate this clock. You only have one oscillator in your embedded system board. Okay, and it probably is about 20 megahertz or whatsoever. Now, how can you manipulate this clock oscillators to give you a 1 second interval? Okay, so that is something that we're going to cover in depth also, and you can use it to count, do a lot of stuff with timers. Okay, so timer is actually a very big topic. In fact, it's about 20% to 10 to 20% of the amount of stuff that you need to learn about this unit. Okay, so you need to know how to do timers. What are timers for? We will discuss. But for this week lecture, you just need to understand that timers are important for creating an interval, 1 second interval, 2 second interval, so on and so forth. Okay. Watchdog timer, like what I explained, it helps you to reset the device. Okay, so if your device has been hanged for some time, it will help you to reset. It will help you to go into the reset address. We discussed on the computer cycles. Computer cycles will fetch, decode, and execute. It continuously do this, but sometimes it gets hanged. Your watchdog timer will be able to help the CPU to reload the reset address, okay, and the CPU will actually go into reset address to start all over again. Now this is very important because a lot of times your devices, you cannot go to the field and check every single embedded system that you have programmed. It's not feasible. Okay, communication device, okay, SPI, USB, all these are communication device. All right, so as I explained, the mother of all communication formats are serial and parallel. So there's only basically two: SPI, I2C, I2C, USB. They are all versions of slight variations of serial communication. So you can see that it's a form of evolution. Okay. Why? Probably you can do some revision. Why do people prefer USB nowadays as compared to SPI, I2C? Okay, so there is a reason. It's very convenient for lay users. Okay, for people who do not know computers, USB is very simple. It's a plug and play device. that enables you to continue to expand virtual ports. Okay, so USB is very good in that way. That's why it's very flexible for people, for non-technical people. Okay, but sometimes this USB is very dangerous for critical devices like devices. So that's why SPI, I2C, USB, they are all forms of serial communication. Okay. Now ADC means analog to digital converter. I hope you can still reflect back what is analog, what is digital. Okay. Now analog, it's 0 to 5 volts. Okay. Now let's say for example my sensor out 4.7 volts. Okay, 0 to 5 volts. Okay, range, and I need to convert this range into 0 to 255. Okay, so there are 256 steps. It means that it's actually an 8-bit. Okay, so when it's 0.00 volt, the equivalent digital information would be 00. But if it's 5 volt, the digital information would be 111111 or FF. All right, FF hex. All right, so there's what we call analog to digital converter. Digital to analog converter is the opposite. Means to say that you have an information 1111 and you need to output 5 volts, okay, into whatever actuators that are doing the work or whatever. Okay, so you ADC and DAC, it's two different things. It's the inverse of one another. Okay, ADC, you need to design it in such a way that you need to do signal conditioning. Okay, optimize the steps. All right, so if I have a device, okay, and I'm actually asked to design an ADC system to be able to cover this range, okay, steps. So these steps are what we call precision. Okay, now 0 to 5 volts can be only represented by 256 steps. Okay, so if 0 to 5 volts divide by 256 steps, that is the amount of precision that you have. You cannot have higher. Okay, can I have higher? I would like to have higher. I would like to have 1024 steps. Okay, for 0 to 5 volts. Okay, so I need to do conditioning in that case. Okay, okay, so these are include monitor development peripherals, means to say that debugging circuits. Most of the embedded systems today that you have, they want to minimize these kind of things. But if you work with commercial products, like for example, back in those days when I was studying embedded system, we do not have a board like MSP430, okay, or Arduino. We do not have those kind of things. If we want to develop, we need to buy the chip and we need to design the whole board for our purposes, right? So those days you need to have a lot of all these kind of things. You need to have a circuit that debugs, all right, these devices, this MSP or whatever chips that you have. Nowadays, everything is done by the compiler. It's very convenient. You don't need to have external device. But those days, this is critical. If you want to convert code into a functioning microcontroller, you need to have this debugger. Okay, debug. So debug. This thing is very critical. Okay, so most of the devices do not use this anymore. It's not so relevant today. But just to tell you that there is this thing, you want to do programming or whatever, there is this debugger. Okay. Okay. Now, how do you access the I/O? Okay, let's say for example, I want to know whether this I/O is doing something, whether this I/O, this LED connected to this I/O is currently on or off or whatsoever. Now there are a couple of registers or memory that are associated with the I/O. Okay. Now take out your MSB, you will be able to find that your MSB have probably 40 pins. Okay. Now each of these I/O pins, the status of this I/O pin is connected to your memory. Okay. So whether it's your memory is the output is currently 1 or 0, you can know the status by looking at the the memory location. Okay, so I want to know, for example, whether that output at the moment is 1 or 0. Okay, that particular pin, I can actually go and access a memory. I'll be able to find, okay, this register is 1 or 0. In fact, I think that is something that you will cover in your labs. So each I/O is associated with one memory in your system. Okay, you want to check the status, you just have to look at that memory. That memory will tell you everything. Okay, now with respect to coding, I will actually cover this in the tutorial. What do I mean by I/O interface with memory? Okay, how can I set the memory I/O to be 1 or 0? How can I know the status? How can I set it into input or output? How can I know the status? Okay, so all this we will cover in the tutorials. This part is a bit technical. I want you guys to focus on this I/O interface. Okay, so this picture shows everything. You have your I/O device, okay, and you have your interface. Okay, so this interface is basically a memory slot in the embedded system. Okay, you have CPU, I/O device, and then you can see that this 27, okay, represents a status for this I/O device, or one of these memory will be able to make this I/O either 1 or 0. Okay, so this picture actually summarizes what we're trying to discuss. In short, every single I/O device is connected to a set of memory that shows its status and several of the status. So you need to know, do not confuse yourself. After we go through the tutorial, you will have a better picture of what we're actually talking about. Okay. Okay. So you have also buffer, latches, drivers, and so on and so forth. Simple example I give you is your printer. Or your serial port. Okay, your serial port actually have a buffer. It receives information to the buffer and then it sends out latches, drivers. These are all things that are actually important, because if you don't have a buffer, communication fails. You fail to do your work. For example, printer. Okay, so normally printer you will have a buffer. All right. So microprocessors like Intel, this is an Intel board, 86 Zilog have separate address for memory device. Okay, microprocessors are complex device. Microcontrollers are simpler device. That's it. All right. So microprocessors normally they have a separate address, memory address for memory and for I/O device. Means to say that if I create, let's say for example, a stack of memory, this type of memory that can be created is different from the I/O device memory. Okay, the devices that are the memory that are associated with the I/O device are different. Their location is different. They are separated. Okay, so this strategy is called standard I/O or I/O map I/O. Okay, so if you separate out, means to say that this is a standard I/O. This requires special instruction and control signal to indicate when an address is intended to the memory or I/O system. So when you want to access, let's say for example, you want to write something on the memory, you need to do certain things in the code to access the memory or the I/O. I/O device can also be included in the memory space. Now this one is a different scheme. Means to say that in this scheme they all jumbled together. All right. Normally simpler devices, microcontrollers, they have this scheme, probably cheaper to manufacture. Okay. So the memory location, a stack of memory, okay, whether it's accessible memory or whether it's associated with devices I/O, they are all jumbled together. Now this scheme is what we call memory map. Okay, standard I/O map or memory map. So this thing can come out as a question. If you do not understand my explanation, you can send me an email. I can explain, reinforce one more time in the next tutorial or the lecture. Okay. Okay. Now this is slightly, we've studied this. Now this picture is depicts it actually even further. All right. The most general view of an I/O interface includes lines. Okay. You have your buses, then you have your memory interface. Okay, and then you have your connection with your I/O. So you still need to access the buses and so on and so forth. This is actually going more and more in depth. Okay, so all you need to know is that more or less you have your CPU, your bus, you have your memory associated with your I/O, and then you have this. Okay, so this picture is just an expansion, more detailed version of the previous picture. All right. So this is an explanation. How does least significant bit, the selection of the I/O device, how are they done? Okay, so you can actually study this on your own. You want more information and narration? Please read the book. Okay? The book that I've actually given you in the Moodle. Once you read, you'll be very clear. Okay, rather than me explaining in cramping everything in 1 hour lecture, it won't be feasible. All right. So please read. And internal registers you have, okay, similar to your memory, because this thing is also a memory. You have your control register, you have your status, and you have your data. Now, what this is trying to tell you is that each of the memory associated with the I/O, okay, you can check these three things. You can check the control register. What is the control status? The status, okay, of the register, whether it's occupied or whatever, whether it's currently 1 or 0, and you can also find out, you know, the data of that register. So register means memory associated with the I/O. Okay, you don't have to confuse yourself with these terms. Register means the memory associated with the I/O. Okay, if you cannot understand, join my tutorial. I will demonstrate to you what is the meaning of all this. So no need to confuse, just go through with us. Okay, allowing, okay, nothing much here. Okay, so this is an example of the status of the register, the I/O device. Okay, so the status, what is the status of that I/O associated with this memory? Okay, so just now we mentioned there is a control, there is a status, and then there is a data. All right, so in the status we have device ready, error, and others. So you can see in that device you can find out all this information by accessing that memory associated with the I/O. Okay, so I give you an example. Your device, you have your I/O. Okay, so there are ports, port A, port B, port C. You can check all this information by accessing the memory associated with that particular port. Okay, what about data? Allow for exchange of data with the device itself. You can actually copy the information, okay, to the I/O memory associated with that I/O. Okay, so these are all the information that we can, if you're confused, just what you can check is that in the memory, there are a couple of information that you can extract, okay, which are consists of control, status, and the data. These are the things that you can access through the memory associated with the I/O. Okay, so again, this is going a bit deep, but bear with me. I will cover this in the tutorial so that you have a clearer picture. Okay, I will go code based, okay, on this thing in the tutorial so you can have a better understanding. Now, this one we've discussed, give you a brief overview. Now you have your parallel interface, your serial. When you're communicating with the device, you can communicate either using parallel or serial. Okay, so parallel, disadvantage is more pins. Okay, if you have 8-bit communication, you have 8 pins. If you have 16-bit communication, you have 16 pins. So imagine the size of the ports. How long will that port be? That port will probably be in inches as compared to your USB that is actually very small. So that's the disadvantage of parallel and the advantage of serial communication. But when it comes to serial, you have to have certain protocols, okay? Especially when you want to communicate with multiple devices, you need protocols, okay? So RS-232 is an example, is a classic example. In fact, you go for embedded class. First thing teach you RS-232 is the most basic serial communication. I think some of you might refer it to a 9-pin serial communication port. Okay, so this port you only need, if the very basic for it to work, you only need, wait, 1, 2, 3. You only need 3 pins for this RS-232 to work. Okay, you need a transmit, you need the receive, and you need the ground. You only need 3 pins. Okay, so those days I actually love this device because it's so simple as compared to digital communication. You have I2C or whatever, very complicated. Okay, but serial communication is very easy to use. Okay, and a lot of military device still use this because it's the most basic serial communication. Okay, now this one you have to learn. Okay, I will cover this more over the time. Parallel interface, you come up with different PCI bus and all this. PCI bus, I think you can still find it in certain of the laptops or whatever, but it's slowly also dying off. Okay, so check it out. These are all stuff in your PC that you do not know. PCI bus, you know. So that's a parallel interface. Serial interface has also evolved. USB, Flywire, SATA, all these kind of things. These are all anything to do with two-wire communication system is a form of serial communication. Okay, so it has evolved into SPI, I2C, PCIe. All these are basically versions of serial communication. Okay, so you have your, normally when you have serial communication, you have buffered input, means to say the whole the data can only read input present at that instant. Latch input means you hold the data until it's read, after which they are usually cleared or ready for another input. So these are the normal conventions when you come to serial or parallel. Okay, both have this. Okay, so output ports register may be written. Okay, so this is something that we also cover. Output ports, input ports. Okay, and then they have this thing called tri-state. I don't know. I think it's somewhere here. Doesn't matter. Okay, output ports register may be written or read, and depending on hardware design. So these are when you deal with, say that for example, your MSP 430, you have your port A, port B, port C, so on and so forth. How do I access information from the various ports? Okay. Timing and synchronization is important when you have multiple devices. Let's say, for example, you have I2C. That's a classic example of synchronization. You have a single I2C, but you want to communicate with multiple devices. Okay, so for our level at this point, we need to know how do we do synchronization. Okay, and then we also have this thing called pooling or interrupt. How does the CPU check the status for the device? Okay, you have two methods. It's called pooling or interrupt. When you pool, you normally pool you use a main program to pool. Okay, so for the main program, in the main program, you will check probably every round of the main program. Okay, but interrupt, it's free. It frees the main program to do other stuff. So in terms of efficiency, power efficiency, interrupt would be much more, much better. All right. Again, a lot of stuff to cover this. Probably I'll break the tutorials into two sections. We have a I/O device. You have pooling and all these kind of things. I'll try to cover all that. I think it's better understood with an example. Okay, so at the moment you just accept it. Okay, read the book one round. I will come up with real applications in the tutorials. Okay. Okay, nothing here. Okay, so bus. When it comes to communication, timing protocols, a set of rules describe how to transfer information. Even serial have it. Okay, but this timing diagram is more important in multiple device like I2C. One master is communicating with several slaves. How do I do that? Okay, so this one is more important. Okay, so normally we only know the line that we only know whether it's 1 or 0. Okay, like for example I2C, you have a common bus, and that bus normally it's 1 or 0. But in order to design this thing in a very practical manner, sometimes you have a third state. We call it the high impedance state. So high impedance state is neither 1 or 0. Okay, it means that there is no signal in that particular bus. So this bus communication is very important. It relates to all this topic that we're discussing, whether it's single device communication, multiple device communication. How do I synchronize two devices together? All this come in a package. We call it timing. Okay, so this timing diagram, I think you've seen in your foundations of digital design. You've covered a bit, and this timing diagram, we will take it back in the this lecture, and we will discuss even more in depth. Okay, especially single device controlling several devices. All right, so this is what we call high impedance state. You have your low state, you have your high state, and then you have your high impedance state. Okay, so this device, whether you can read or write, okay, you have to do it only at certain time. Okay, when the address reaches high or the data reaches low or whatsoever, there is a specific window for you to write and read. Okay, so it depends on this timing. Okay, so timing diagram shows you when must information be sent, when must information be received. All this has to do with the protocol. Okay, so that's why serial communication has very minimal protocol. SPI and I2C have more protocol, but they have more complex stuff that they can do, communicate with multiple devices. This is something that normal serial RS-232 cannot do, right? So I think that's about the lecture that we have today. I think this week's lecture is a bit more complex. I will cover as much as possible in a tutorial. If I cannot do it in one tutorial, I'll break it into two, okay? Because there's a lot of stuff today. Please read the chapters in the book, okay? The IO chapters. I will extract some of the stuff from the book also. So I think that's all for this week. I'll see you guys. Any problem with the labs, please let us know, okay? So see you guys.